Hello, today we continue with our normalization program for QED, and the next step in this calculation is to get the first order, the first loop contribution to the electron self-energy, right? So we're looking today at the 1pi contributions to electron propagator, right? So the very first loop we have to figure out is this one, right? And we know that the divergences here, the renormalization of this contribution will be given by this counter term, right? Of course, there's other terms, but they are all higher orders in the coupling constant expansion, right? So I'm naming this very first loop in which the electron emits and reabsorbs the photon sigma 2. And 2 here means this is order E squared, right? So let's write this loop, right, using the Feynman rules for QED and start calculating it. So there's two powers of the vertex, right, the QED vertex, which gives me this minus IE square. There's a loop, and I choose the loop variable to be k, so there's a d for k over 2 pi to the fourth, right? And then the loop itself, and I have to give some Lorentz indexes to that, but that is summed with the photon propagator. So just call the first one gamma nu. Then I have the fermion propagator given by k slash plus m over k square minus m square. And I should have a plus I epsilon here, but I'll be ignoring these factors, right? We know where they are when we need them, right? Just to keep the notation clean. Then another Dirac matrix, gamma mu, right? And then the photon propagator, which is minus I g mu nu. It's contracted with both these matrices at the ends over p minus k square, and I should have a plus I epsilon. I'm not putting here. What I am putting here, which is different than we did before, is just some fictitious mass for the photon. And the reason I'm doing this right here is that this diagram has a divergence. You can even see it here, right? If I don't put this one, there will be a divergence for very soft photons, right? If this momentum goes to zero, this will be possibly blowing up, right? And this is another, once again, an infrared divergence, right? We mentioned this before when we were first talking about this diagram or this 1pi function. And I don't want to deal with the infrared divergences right now. I'm focusing on the ultraviolet ones. So for now, I'll just put this term here. At the end, I'll take it to 0. And then we'll have essentially regularized the infrared divergence, right? I'm putting that divergence in terms of this parameter, right? Which you could think of as a infrared regulator, right? So it's not a real mass for the photon, it's just a regulator for that divergence, right? Now I want to use all the same tricks we used before. The first one would be to do Feynman parametrization for these denominators. Let me write it here. K squared minus m squared times 1 over p minus k squared m gamma squared. I can write in terms of a Feynman parameter, call that parameter x as usual, and that becomes a big denominator, which is k squared minus 2x k times p plus x p squared minus x m gamma squared minus 1 minus x m squared. Let me extend that a little bit. And all of that to the power square, right? This is very similar to the denominators we had before, right? Especially the cross term between k and p. We need to do change in variables to get rid of that cross term between k and p, right? I'll do that here. So just make up a new momentum called L mu, and that's k mu minus x p mu, right? And I'll put that here, and that becomes just a simple integral, a simple denominator in L squared minus something that does not involve L, right? And that something in this case is just, let me write it here. I'm using that gamma here to indicate I have this infrared regulator. If I take that mass, that fictitious mass to zero, then I can just remove the gamma, right? And this is defined by all of these. After I complete the squares, will be just 1 minus x m squared minus x 1 minus x p squared. This m squared is the mass of the electron, right? I hope that was clear from the start. And then I have the term that comes from here, x m gamma squared. So this is the definition of this guy. It will be appearing everywhere, right? And that gives us the Feynman parametrization. We can go back with this to the integral upstairs there, and also do the same change in the numerator. Let's copy it down here, right? So this G min u already makes one of these guys contract with each other. There's a bunch of powers of I here, there's an I here, I squared there, that all amounts to just minus e squared, right? These numerators I have Feynman parameterized, so I can put an integral in dx from 0 to 1 out here, and L squared minus delta gamma square right here, right? And that has become dl. Now k slash, right? K slash here will just become L slash plus x p slash, right? Just have to solve this. But L slash is odd under this, it's an odd function of L mu, right? So it's the integral is 0 because I don't need these odd terms, right? They are just 0. So I can just replace k here by x p slash, right? That takes care of all of that, of doing the Feynman parameterization. Right, let me just check. Everything is okay. Now, what I want to do is dimensionally regularize this integral, right? That's why I'm avoiding messing with these Dirac matrices, right? In principle, there's some relations we could use here, but they change if you go away from 4 dimensions. So I want to dimensionally regularize before I do that. So let me copy the expression here just to apply the dimensional regularization, and you can compare both expressions. So one of the things I want to do is to introduce this term mu to epsilon, right? Remember, epsilon is 4 minus d. So when d goes back to 4, epsilon goes to 0. And the function of this guy is, again, to keep this coupling adimensional, right? I'm not changing the dimension of the whole integral. This changes to d, right? So I'm now integrating in d dimensions. So both of these guys become d. And now I have to worry about these Dirac matrices, right? I have shown when we were doing the photon self-energy, right? I have shown some relations that were useful when you go away from 4 dimensions. So one of them was just this, that if you take a gamma matrix between a Dirac matrix between two others that are contracted, which is exactly the situation going on here, right? With this p slash, there's a gamma hidden in here between these two which are contracted, right? You have a relation that in 2 dimensions is just minus 2 gamma alpha, right? But in d dimensions that gets changed to 2 minus epsilon gamma alpha, right? So that this p slash will become, so gamma mu p slash gamma mu, which we have right here, will become just minus 2 minus epsilon p slash, right? I'll have to substitute here. Also, I have this other piece with the mass here that essentially just has the identity in the Dirac matrix space, right? And in that case, I have to figure out what the gamma mu contraction gives me, right? We didn't show that relation, but we did say that we can still keep the algebra for the Dirac matrices like that, right? This one is still true in n dimensions, and if you contract g mu on both sides of this equation, just contract it here, actually with indexes down, mu g mu here, and you can quickly show you have twice g mu on both sides of this equation. This is d in d dimensions, and that means that this gamma mu is d, because you have 2 gamma mu here and 2d here, so the 2 conceals in both sides of this equation. You have this one. So with these 2 in hand, I can come here and substitute them and simplify this integral, get rid of the Dirac matrices that are there, right? This becomes, let me copy it here, right? Let's remove the colors. And this part just becomes, let me erase this, stretch it a little bit. And now this becomes just minus x for this part, right? This is the minus 2 minus epsilon p slash using this relation. And this one, I just get d times m, right? Using this one. Now, this is what I get from dimensional regularization. There's not much else to it. Now I want to follow the tricks we have been learning and Vic rotate this, because that will allow me to do the integral, right? So Vic rotation. Now I change this L to a L Euclidean, right? Same here. In this case, there's a minus sign. In this one, there's a complex I coming out here, right? So I'm rotating all to the Euclidean. And this one I can just rewrite in this way because it's to the power 2. So that sign does not come out of the expression, right? Let me rewrite this guy also for convenience in terms of epsilon, because otherwise I'll have d and epsilon mixed there, and it's easier to just have one of them. Okay. So that's how it looks like. right? And this integral is very similar now to one we did also in the photon self-energy calculation, right? We had two there. One was LE square over this denominator, and another one was just 1 over this denominator, which is exactly what we have here. So I can use all the same calculations we did. That was 2 videos ago, and this is just let me copy this part. There's a 4 pi to the power d over 2, right? We know how to integrate this. It will give us some gamma functions, right? Can return the color of this. The Feynman parameter integral is still there. Now this numerator I can bring out here. We will just 4 minus epsilon mass minus x 2 minus epsilon p slash times the result for the integral, which is gamma of 2d over 2 minus 2 minus d over 2. Another piece just is already out here. And of course you have this gamma, which is this delta gamma square to the power 2 minus d over 2. Again, I won't repeat that here. I can expand these terms that involve epsilon for small epsilon. Can do that by hand, or put it in mathematical, like I have shown a few times already, right? It doesn't matter. It's again the same expression we had before, but now multiplied by these terms. So you see there's some epsilons here. So when they multiply the 1 over epsilon that is coming from here, these parts will contribute to the finite part of the 2-point function, right, to the 1pi function. And so I have to keep these epsilon terms here, right? Let me write first the expansion of the other part that we know. So this is minus IE square over 16 pi square, which is the usual thing you get here, the Feynman integral parameter. And now all the expansion in epsilon. Let me just copy this for now. I'll need more space, so let me move it to the left. And this is what I get from everything else when I go close to 4 dimensions. So the UV divergence is here, right? You have all these usual pieces, so the Euler-Mascheroni constant, some log of 4 pi. There's a log of this guy over mu square. So delta gamma square over mu square. By now this should start to be getting familiar, right? Because it always looks like this same expression for dimensional regularization. And of course there's ordered epsilon terms, which I can ignore already because I'm multiplying just by other epsilon out here, right? So there's still some finite parts that come from the multiplication of these two, right? The multiplication of these epsilons by the rest of these constants will go to 0, right? There's just linear in epsilon. I can take it to 0 eventually. One trick that I want to do here that I didn't do before is the following. I can take this log, right, and rewrite as the logarithm of mu over delta gamma square, right, with a sign in here, plus. But then this mu, I can group with this, right? I can bring this log of 4 pi here. Let me get some space. So I have a mu here. I can bring this 4 pi in here, right? And this guy, I can exponentiate, take the log of the exponential of this guy, right? And just put an exponential of minus this constant here. These are all just numbers that I can group with mu and call these just the log of mu tilde square. I had mu square, I'll call this mu tilde square over delta gamma square. That's a way of putting these numbers together. I mean, this is an arbitrary number, mu, right? So I can group it together with these other constants here and just simplify my expression a bit, right? Now, if I want to separate the divergent part from the converging part, I can multiply these two expressions, right? This I can rewrite. This one I can just remember e squared is 4 pi alpha, so I can put that here, will be just minus I alpha over 4 pi, because there's a factor of 4 pi that I absorb up there. And as to the rest, I want to do this multiplication and then throw away all the terms that are linear or higher powers in epsilon. That will give me a 4m minus 2x p slash. So the multiplication of these by these, right? This is the diverging part. It's 2 epsilon. So I take the terms that are independent of epsilon here, multiply by these, is the diverging part. Now I have this log here multiplied by the finite part in this side is just 4m minus 2x p slash log of mu tilde square or delta gamma square, right? Now there's the part proportional to epsilon in here, multiplied by 2 over epsilon. The epsilon will go away, and that will give me a finite part, which is x p slash minus m. And then everything else is just order epsilon, which I can forget eventually. This goes to 0 in 4 dimensions. So for now, what is important to us is that this is the diverging part right here. Let me just quickly check I didn't make any mistake. No, looks fine. And then finite terms, right? This diverging part is easier to integrate. That will be useful for us later. So let me write. After all, it's just an integral in x for this guy. This one doesn't even depend on x. So it's really simple integral, right? I can remove a sign out here. It's just I alpha over 4 pi times p slash minus 4m over 2 epsilon. So this is the diverging part, and of course there are finite terms. Let me fix the font here, right? Plus finite terms, which have a pretty complicated integral to do because of this part, right? There's x's hidden in here, and that gives you a big analytical expression if you try to integrate, right? But we managed to calculate, and keep in mind, this is minus I sigma 2 of p slash. So there's an I here because that's how I define the loop, right? So the same I there. Now we can proceed with what we call the on-shell renormalization scheme. that consists in a particular choice for the renormalization conditions, right? So we had two normalization conditions, one that is determined at some value of p slash and fixes the position of the pole for the full electron propagator, right? And another one that fixes the residue of that pole, right? This is called at p slash, when p slash goes to some value, p slash 0, right? And these need to be 0, fixes, this one fixes the residue and this fixes the position of the pole. The on-shell renormalization scheme is to choose this value to be just the physical mass times the identity in that space of Dirac matrices here and here. So I'm demanding that the pole is in the physical mass of the electron and the residue again is 1, right? Remembering that this sigma, the complete sigma, is given by this sum, right? Let me go all the way to the top here. So sigma is just the sum of sigma 2, right? There's a minus between these two, right? So the sigma 2 minus this contribution. So I can write this here. Sigma of p slash is just sigma 2, which is the loop, one loop contribution, minus p slash delta 2 minus delta m, right? These two conditions will then imply, for instance, the second one will imply that the p slash of this is 0, right? There's only p slash here, and of course there's the derivative in p slash of this one, and that gives me delta 2 as just the derivative of sigma 2 of p slash. Of course, this is calculated at p slash equal m, so this one is also p slash equal m. Right, so delta 2 factors is only dependent on the derivative of this guy calculated at this point. So that's the first one we will calculate, right? And then once we know that, right, once we know delta 2, we can go back to this other condition and write that sigma 2 of m, right? I'm just using this one here, right? Minus m delta 2, because I'm substituting p slash for m, minus delta m is 0, that condition up there, which allows me to solve for delta m as m delta 2 minus sigma 2 of m. Right, so these two equations will give me first delta 2, I'm doing that first, and then once I know delta 2, I can get delta m, right? We could do all of this by hand, but again, I think we save time and energy by doing it in Mathematica. So in order to get delta 2, the first thing we'll need to do is to calculate the derivative of sigma 2, right? PS here means p slash, so everywhere you see p slash means PS, it means p slash. This is the whole expression we just derivated for sigma 2, and this is translation of this expression to Mathematica, right? So I grouped all these constants as the log of mu 2 the square, right? That's what this means. Delta 2 here means delta gamma square, right? And so this is the expression, and I'm exchanging e squared by 4 pi alpha, right? So now we can, just to make things clear, define sigma 2 of p slash, right, as this expression right here. Let me put this here and run it, right? And I made a series in epsilon to see how it looks and separate the divergent part, as we have seen before, from the finite part. So this one we have written, right? It's just the diverging part, but now we have also here the finite part explicitly. And also I have delta 2 here, which I'll eventually have to substitute by its full expression. So I'll create a substitution rule here for that, which substitute this delta 2 by the expression with everything in there. And of course, once we make p slash go to m squared, I'll substitute that right here, right? So now I want to take the derivative. So I'll define another variable. So I call this sigma 2 of p slash. I'll call the derivative d sigma 2 of p slash, right? And this will be just the derivative of the first one, this one. Of course, substituting delta 2 with this substitution rule, because there's also a p slash here. I have to substitute before I differentiate in relation to p slash. That is the expression. I can simplify it a little bit, maybe. And that's how it looks like, right? It's not very useful like that, but that's it, right? And also I need, and I'll call that d sigma 2 of m, the same expression, but I substitute everywhere p slash for m, because remember delta 2 is equal to this derivative in this point, right? So I have to define that too, and this is the expression I got, right? This is equivalent to what I obtain analytically, right, in the lecture notes. So in the lecture notes, I did these derivatives by hand and got this expression, which is the same that is up here, right? You have to actually simplify it a little bit to see, but that's the same expression, right? So now what I want to do is the integration of this function, right? This is just the integrand. You see there's x everywhere. I would, in principle, have to run this integration command right here. It takes a while to run in Mathematica, about 10 minutes in my computer, so I won't do it here. I can show you the answer, right, which is this one. Right? It's pretty complicated expression, right? It's already run and loaded into this variable. So it's the derivative of sigma 2m integrated, right? Is here. Again, the same expression as there, just written a little bit differently, right? And that's what I need to this is delta 2, essentially, right? Of course, put it in this way is hard to see anything. But remember, this m gamma here is the mass of the photon, right? Which is just a regulator for the infrared divergence, right? This is a small number which I'll take to 0 at the end. So what I can do at this point is actually do a series in m gamma. So I can take this result for the integration and take m gamma going to 0. This is just conditions to guide Mathematica, right? I'm saying everything is bigger than 0, all these masses and parameters here, right? And the refine will make it look good, right? And here is what I get. So now you can see, right, there's still a infrared divergence here. So when m gamma goes to 0, these diverges, right? It's the infrared divergence. There's a piece here that I can take to 0 safely. Mathematica didn't do it, but I'll do it for him, right? So I can just take this piece and send to 0, right? Like that. And I'll call this delta 2. And there it is. And if I want to take a look on how delta 2 looks, I can factor out this epsilon, right? I can just expand this expression and then collect for epsilon, right? And that looks better. And this is the expression we wanted, right? Which then gives us this expression, right? So you see here the expression for delta 2, right? We found the first counter term, and both divergences are here, right? So this is UV divergent, right? But also infrared divergent, right? You can see that if I take M gamma to 0 here, this part blows up, right? And we should not forget about this infrared. We'll deal with that in the next video, the one after that. Right? Now we have to go back to delta M, right? But that involves also calculating sigma 2 of M, right? So sigma 2 of M is just the one loop function, but now substituting p slash for M everywhere, right? And the expression you get if you do that is just M alpha over 2 pi. You remember there was a lot of p slash and m terms here. I just put m everywhere, and that becomes just 2 minus x, 2 over epsilon, that's the diverging part, right? Plus 2 minus x log, again, of mu tilde square over delta gamma. Keeping in mind that this delta gamma now, it's implicit. When I mix delta gamma of p slash with delta gamma of m, I'll make this more explicit. But there is a p slash in here, and so this delta gamma square is really the delta gamma square of m. So I'm substituting p slash for m in there, right? And there's also another small piece here, which is finite, that is still here for p slash equal m, right? So this is the integral I want to do. Again, we save a lot of time by doing this in Mathematica. Let me change to that, right? And now I have to run that in Mathematica. So let me start by loading up sigma of p slash, that's the integrand, right? Now I want to define a sigma 2 of m, which is just this guy, but I'll substitute p slash for m everywhere and simplify, right? And this is what I need to integrate now, right? Wait, no, I'm missing one piece here. Forgot to substitute delta, right? So before I do the substitution here, I need to do this one. So here, first I substitute delta inside sigma 2 of p slash, then I make the other one, and this looks better, right? Yeah. So now, in principle, I want to do the integration here, right? Once again, the command would be this one. I just integrate that from x going from 0 to 1, and these assumptions is just to help, right? But that takes a while. I have the integral done here. I call this integrated, right? And this is the solution. Again, very non-enlightening contribution, right? But I can, again, think on what happens if I take m gamma going to 0, right? In this case, this part should behave well. There's no infrared divergence here, right? So if I just take the limit of m gamma going to 0 instead of the series, and then refine just to simplify the expression, right? It should be okay. And then the expand and collecting here is just to express this in a simple form. Let's see what it does. This one takes a few seconds. I hope I don't have to cut the video. And there it is, right? So that's a pretty simple expression, right? And that gives me the sigma 2 of m, right? Which is written right here. And you see it's regular. I actually took the limit of this going to 0, and I have no infrared divergences right here. So now I have this expression for sigma 2. It's a simple matter of calculating delta m, which is given by m delta 2 minus sigma 2 m. So I just have to take this expression up here, multiply by m, and then subtract this one, right? Which is pretty easy. There will be some cancellations between those logs, and delta m will be just minus m alpha over 2 pi, right? Because I have this common factor on both of them. Remember, delta 2 will be multiplied by m, right? And then I just have to add everything else. Is 4 over epsilon plus 4 plus 2 log of mu square over m square plus the log of m gamma square m square. So you see that's another counter term, and it contains both UV and infrared divergences right here. Now, that allows me to go back to the expression, right? We know that sigma is given by this, right? It's just this expression. I can rewrite it down here. Let me put it here, right? And write it explicitly. Of course, there's other terms, but at this order in perturbation theory, that's what we get, right? And I can write now this sigma 2 of p slash, and then I just use that this delta m is, I expand delta m using this expression, right, to write these in this way. So there's a sigma 2 of m here coming from this piece right here, right? And there's another piece coming from the combination of m delta 2 that appears here and p slash delta 2. So I can write these as minus p slash minus m times delta 2, right? Now, in principle, I could use the results I get for this guy and delta 2 here, right? The integrals I just did. But then I would have to integrate this guy for any p slash, which is really complicated. It's easier to actually go back a few steps in the integration of x, right, in the Feynman parameter of these two terms, and actually group them together. So I can write sigma of p slash, right? And then this part, let me color it green and color this one blue, right? This part will actually be given by an expression where a lot of things will be simplifiable, let's say like that. So let me make things a bit smaller. Now it's a big analytical expression, right? This is the integral in Feynman parameters. So I'm taking this guy before I integrated it, right? There's a common factor of 2x, and then everything will be used before I substitute p slash for m and after. So there will be a lot of factors that look like p slash minus m 2 over epsilon. Remember, in this guy, there's minus 2p slash over epsilon. In this guy, minus 2m over epsilon. And there's a minus sign between them, right? So that's where these kind of terms come from. You know, we have a lot of these. So log of mu tilde square. I'm separating mu tilde from the delta because the delta, there's two versions of delta, which I'll write soon. This is p slash plus m, right? Minus m, sorry. It's the common term. And then the delta part. Let me move this up. Remember that delta was given, delta gamma square was 1 minus x m square minus x 1 minus x p square plus x m gamma square, right? I'll be calling this guy gamma square of p slash, but then there's another guy, which is this one, right? Which is just substituting this for m and simplifying a bit, is 1 minus x square m square plus x m gamma square, because I can group these two. Once I put an m square here, I can group those, right? So keep that in mind. I'll use these two definitions here. So this is actually p slash log of the one without substituting. I'll put it like that. Minus m the log of the one calculated at m. And then I can close the whole thing here with this one, right? So that's the expression for the green part here. And I also need to put the expression for the blue part, in which I just take delta 2, the derivative of, which is just the derivative of sigma 2, right? Calculated at p slash equal m, right? And multiply by this factor, right? So let me write the blue part here. It's just, again, I have the same factor in front, same integral, same factor of 2x. And I'll just take the expression of that derivative and multiply everything by p slash minus m. And you see a lot of factors that are just like the ones up there, right? Which is why this is useful. So you just have to go back and look the expression for the derivative before I actually integrate, right? So p slash minus m log of delta gamma square calculated m, because this is coming from delta 2 here, over mu tilde square. And there's a big part that appeared after taking the derivative. Okay, so I have these two terms which are subtracted, right? I have these minus this one in the bottom, and you can start seeing the simplifications, right? So this term goes away, right? This one, 2 here, right? The log of mu to the square, right, is here and here. You see the sign is opposite between them. So if I bring them to the numerator, this goes away, right, with that. And this part, right, the part that has p slash does not go away, because here I have p slash log of delta gamma of m. But the part with the mass, this one, actually there's a cancellation with that. So the part with that mass go away, right? And then this part stays and these logs stay. I can put those together, right? And this is just sigma of p slash will be just alpha over 4 pi. The integral stays. And then I have the part, let me bring it down so you can see, right? The part with these logs will be, there's a p slash here and another p slash here, so I can put these two logs together. There's a relative sign between them here, so that's just the log of delta gamma square p slash over delta gamma square of m. And then this whole thing here with remembering the sign, let me bring it down over here. And there you go. So this is the fully renormalized in the on-shell renormalization scheme form for the 1pi function of the electron, right? The self-energy of the electron and one loop, right? There's a few, again, this I can do this integral in mathematics. I'll show it really quickly in a second or two. Again, the analytical expression for the answer is not very illuminating, but a few things you can already see here which are important to notice. So this first term, I can take the mass of the photon to 0 here. This is regular and behaves well. There's still an infrared divergence here that I'll show in Mathematica in a second, right? But the point is that mu went away. This unphysical constant is not present anywhere anymore. It was completely eliminated, right? And also the UV divergence went away. So our renormalization as far as UV divergences is done, right? And that's what we wanted to do, right? I didn't care about the infrared divergences yet. Now, as for these two parts, let's take a quick look in Mathematica just so you see what happens, right? So let me change here and here, right? And so this is the first term, the term with the two logs, right? And this is the second term, that complicated expression there, right? But in both cases, I need to integrate. In principle, I would have to give a command that looks like this, right? This is the integral of 2x times that term. Remember, there was a 2x outside here, right? There's a 2x multiplying term 1 and 2x times terms 2. So that's what that 2x is doing there, right? Again, the integral takes a while. And notice here that I did a condition. In this case, p slash is bigger than m, right? And that I call region 1. If I would do the integral, I won't do it here to not waste your time waiting for Mathematica. That would be the result. So you see that that integral for momentum bigger than the mass develops imaginary part. There's a I pi here and here, right? And that's what we expected, right? In this case, as I said, for T1, right, I took already the mass of the photon going to zero. This is appearing neither here nor there, right? This is delta over delta. And you see the integral converges, it's fine, right? But that means that the branch cut for the production of one electron and one photon, it starts at the mass of the electron, right? Because the mass of the photon is zero. Right? So that integration gives me this expression. And if I invert this, I make p slash bigger or smaller than minus m, because I can just take the momenta going into the other direction, I get the same result, right? So the same would be true if I make this smaller or equal to minus m. So in module, the momentum is still bigger than the mass, right? On the other side, if I put p slash between plus m and minus m, I call that region 2, then I get a real answer. There's no imaginary part to that function, as we expected, right? And this is the result for the integral. Could probably simplify here, but I don't care that much, right? Now T2, if I take the integral of T2, I don't need to separate into regions, right? It's a fairly complicated expression. This is the result for the integral. Again, there's a lot of powers of m gamma everywhere, but I can take this and refine it in this way. Again, Mathematica is not getting rid of this part here in which I can take m gamma to 0. So do it for Mathematica. And then you see it's a fairly simple expression that contains the infrared divergence. It's coming from that second part. Again, I have p slash minus m right here, right, times log of m gamma over m, and a regular part. So that our self-energy, right, the self-energy of the electron is given by this part, I mean that complicated expression that has imaginary part or not, depending on this relation between p slash and m, right? And this other part that still contains the infrared divergence, right, coming from here. One final note in this on-shell renormalization scheme is that you might have noticed that the correction to the mass is proportional to the mass itself, right? We have predicted that this would happen a few videos ago based on chiral symmetry, right? We have seen that if you start with a mass which is 0 in the Lagrangian, that decouples the left-hand part of a fermion from the right-hand part of a fermion, and that makes all the radiative corrections to the mass of that fermion equal to 0, right? This is appearing in this form right here, right? I could easily exchange this m for m0, the bare mass, right? And the difference between m and m0 is another thing that is order alpha, right? Since I already have an alpha here, the difference between them would be order alpha square. And then you see if I put m0 equals 0, delta m will be 0 too, right? And that's consistent, right? It appears naturally here. And it is a consequence of these Lagrangian of the QED being chiral, I mean, having a chiral symmetry in the limit where the mass of the fermion goes to 0, right? As a final point for this video, I want to discuss the so-called subtraction schemes, right? So the same way we did with the scalar and the photon, right? We could have resummed all the 1pi contributions to the full fermion propagator of the electron and obtain this expression, right? It's just the full propagator with the physical mass and some and the sum of all 1pi contributions here, right? In the on-shell renormalization scheme, we set a condition for this guy, right? We said that that renormalized mass we defined in the Lagrangian needs to be the physical, sometimes called also the pole mass, right? Which is the actual experimental mass you see when the guy goes on shell. And that means that the renormalization condition for this guy was that at that pole, right, this guy needs to be 0 so that he is actually a pole of the whole, of the full propagator, right? But that's not the only way we could have proceeded, right? We could, in principle, right, as we know, we defined at some point when we were renormalizing the theory, we defined a delta m, right, which was given by a z2 times the bare mass minus m, right? This is what eliminates z2 from the numerator here, right, near the one pole, the one particle pole, right, and defines these two. And then I put a condition to this guy, which then allows me to calculate that one. See the order of the things here. I'm saying this is the physical mass, and that implies a calculation for this guy, right? That's how we did it so far. But I could have called this just a renormalized mass, not necessarily the physical mass, right? I'll put a R everywhere here because I'm changing the definition, right? So that's a renormalized mass. This is a renormalized delta M, right? Also, since I'm changing everything, the most general thing would be to also change Z2 and invert that logic. I could say, I want some analytical properties for this guy. Now, this is my condition, right? And that allows me to calculate MR, right? What I'm losing now is that this mass has nothing to do with a pole in the propagator, not necessarily a pole in the propagator. So it's not a mass of any particle going on shell, right? Even calling it a mass might be abuse of language, right? This is more like a coupling to a two-point interaction, right? But I could do that, right? And then get this mass, right? This renormalized mass that is not the pole mass, right? Let me write this. I'm calling this guy the renormalized mass. Yeah. So, but why would I do that, right? Why, instead of defining this guy physically and then calculating that one, I want to force some properties on this guy and then obtain this one. Well, in order to understand what we want to do, of course, what I want to do here is to simplify my life, right? At least from the point of view of calculations, right? And demand a simple form for deltas, right? Delta m, and of course that will imply something for delta 2, right? And we'll have a delta 2r now. And what I want to do is to simplify my life by getting a simple form for these guys. And we have just calculated these guys in the on-shell renormalization scheme, and you can see, I guess you could see that these are quite hard to calculate. What we will demand now is based on the fact that, remember, we right at the start we saw that the sigma of p slash, which again is given by sigma 2 of p slash minus p slash delta 2 minus delta m, right, plus higher order next to leading order corrections, right? is given by this subtraction, right? The 1pi function is given by this subtraction. And this guy had a simple form for the divergent term, right? It's the easiest integral in here. Was the one we did first, right? We concluded that this guy is minus alpha over 2 pi times p slash minus 4m over epsilon plus a finite part, right? There's a lot of things here, but the only part that depends on 1 over epsilon is this one. And that's what generates what we call the minimal subtraction scheme, or MS scheme, right? So the idea here is to forget all physical motivation of renormalization, or at least writing my theory in terms of this physical mass, right? And actually just solving the divergence problem, right? I'll just impose that delta 2 and delta m be whatever they need to be to remove the infinity, the divergence from here, right? And make this guy finite. Right? And that's easy to do because now I know explicitly the form of the divergence here. And I just have to say that delta 2 ms, right, is just minus alpha over 2 pi epsilon, right? Because p slash is here and here. You see, I'm just solving this equation so that only the finite part is left, right? So that defines delta 2, right? And delta m is also similarly defined as in the MS scheme will be defined as minus 4 alpha because of this 4 right here, m in the MS, right? So I'm just using these definitions, replacing R by MS, right? So remember that I'm using this scheme. Of course, there's the same 2 pi epsilon here. And the effect of that is just removing the divergence here, right? Just get really simple counterterms in terms of calculation, but now it's harder to see physically what I am assuming here. In fact, one of the consequences of that, now I have to calculate this guy in this scheme, right? I'll just put a MS here, so we remember what we're doing, right? And the thing is that now, since I'm subtracting only this part, I know that this guy will not disappear with that unphysical constant that I have in here, right? And so this will now be dependent on mu. In fact, I can write it explicitly before integration, right? This will be that finite part right there. But that finite part is mu dependent, right? Because I'm not imposing physicality, let's say, on this guy, right? So this will be just alpha over 4 pi integral. I'm just repeating some expressions we have seen many times today. Now I have the mass that appears here comes from the Lagrangian. It's this renormalized mass, right? Which I'm not saying is physical anymore. I'm just exchanging R for a mass, right? Minus 2x p slash log of mu to the square over delta square. I'm removing the gamma for now because we know what happens with the infrared. Divergence will be everywhere there. I just not be repeating it anymore, right? Plus 2x P slash minus M in the MS scheme, sometimes called the MS mass or renormalized mass or running mass, as we'll see shortly, right? And so this is it. In this approach, this is now called the subtraction point, because it is introduced by this subtraction scheme, right? You have to be careful about this because it might seem that this parameter was introduced by dimensional regularization, right? In our approach, it really was, but we are identifying it with the subtraction point when we do that. We could have done it otherwise. We could have started without this mu, right? Just leave the coupling constant with the wrong dimension, right? Go forward in your calculation, you would have some logs here with strange dimension, right? We would have something like this, right? Log of delta. And in the moment we try to define this quantity and do some dimensional analysis, we would have to introduce this subtraction point here, right? So it's really a new constant that I'm using the one that already came from the dimensional regularization, but it's really not qualitatively the same, right? It's also a non-physical parameter for my theory, but it originates differently. In fact, if I did Pauli-Wheeler's regularization, there would be no mu here, right? Lambda that appears in the Pauli-Wheeler's would go away because I would demand these guys to be functions of lambda and subtract the divergence. And again, I would have some log of lambda that makes no sense. If I want to have the right dimensions for this guy, I would have to show up with a mu, right? Which again is the subtraction point, right? So now I have this new parameter that is unphysical, right? Another subtraction scheme, which is very popular, especially almost 100% of the times when you're doing dimensional regularization, comes from the fact that this log hides a lot of constants, right? This is really, forget the delta, right? This is really the log of mu plus the log of 4 pi, right? Minus the Euler-Mascheroni constant, right? And these two guys, this part right here, always shows up when you're doing dimensional regularization, right? Together with the 2 over epsilon, right? That went away here, right? So another subtraction scheme called the MS bar scheme, let me put it right here, actually changes minimally this subtraction to make it so that delta and delta 2 and delta m also carry away these constants. So MS bar scheme defines this guy in the same way, but now I also subtract alpha over 4 pi times the log of 4 pi e to the minus gamma. That eliminates these two parts together with the divergence. So I take a finite part away with the divergence, right? And in this case, same thing for delta m, right? So the delta m in the MS bar scheme will be same thing I had before for alpha m MS bar. So this is the MS bar mass now, 2 pi epsilon minus 4 alpha m MS bar over 4 pi times again the log of 4 pi epsilon to the minus gamma, right? So that's another scheme, but it's very similar. Qualitatively, it's the same thing I did before. Just in here, I have dependence on this mu tilde constant, and here will be really mu, because I'm eliminating the finite part, and I end up with sigma ms bar of p slash mu, right, which is this very same thing. But now I replace m tilde, mu tilde by just mu, right? And this is the ms bar mass, right? Now, suppose I'm doing this scheme for the electron, right? That shouldn't change, right? In any way, I'm just writing the same theory in terms of these other variables, right? Making my counterterms different. But it is the same theory, so it's still true that this propagator that I defined up here, this one, right? Now, in terms of the renormalized constants in the ms bar scheme, should have a pole in the physical mass of the electron, right? After all, if the electron goes on shell, there should be a pole. Now, I'm calculating both of these quantities in the ms bar scheme, but the pole is still in the physical mass of the electron, right? So this is the same, at least near the pole, this is the same as this guy, right? And the other term that went here is 0 near that pole. So that means that the physical mass of the electron should be equal to this ms bar plus the sigma in the ms bar scheme calculated at the position of the pole, right? That allows me to write the ms bar mass in terms of the physical mass, right? So the ms bar mass, which of course, if this guy depends on mu, right? That's the important part. And this guy does not, because it's a number, this is the physical pole mass. That means that this guy depends on this, on physical mu, right? And is given by m minus this, right? Then I can use this expression up here. Let me copy it because it won't fit. I cannot show both at the same time. This will be just m minus this thing, right? I can do a little bit of simplification here. Divide everything by 2. There's a 2 here. This 2 goes away. This one, 2, right? And p slash, I'm calculating this for p slash equal m. M is the physical mass. So this goes to m. Here there's a p slash, it becomes m, right? And here I have an m. Now, the difference between the ms bar and m, right? ms bar, the ms bar mass and the physical mass, right? The difference between them is a correction of order alpha that you can see here, right? So I can iterate that here, and the difference in all these expressions will be order alpha square. So I can remove ms here for m. Same in here, which I had, right? And of course, then this simplifies a lot, right? And I can write this, right? There's a factor m that I can bring to the front everywhere here and write this as m is equal to 1 minus alpha of 2 pi, because I remove this factor, right? Integral from 0 to 1 dx of 2 minus x log of this, and this thing becomes, right, delta square when I take p slash to the physical mass, right, will be 1 minus x m square in the ms bar, right? That's what I had here, minus x 1 minus x. That's where p slash was. That becomes m square. And if I do that approximation, this is just m square 1 minus x square, right? So that's what I put in here. Right? It will be mu square m square 1 minus x square plus, again, x minus 1. I don't need these anymore, right? So you see that the ms bar mass is similar to the pole mass plus a correction, right? There's something that takes it away from the pole, right? But that depends on this mu, right? This integral I can do. It's pretty easy to do that one, right? It's just m 1 minus alpha pi 4 plus 3 ln mu square over m square. So this is usually a bit puzzling, right? First contact with this running mass, and now we call it running mass because there's a scale here. Remember, mu has dimensions of mass. It's totally unphysical, right? But that's a scale that if I change it, this mass bar goes farther away from the original mass or closer to it, right? So it's really like a running correction to the pole mass, right? Which is a bit confusing. Most people see that and say, well, you simplified the counterterms, but now you got yourself a mass that is not really a mass, and that's messy, right? But there's a few situations in which these can be useful, really useful, right? The first thing to notice is that if I take any observable quantity, right, directly observable quantity, that cannot depend on this unphysical scale right here, right? And since the calculation of this constant will involve the Lagrangian, and we have now Feynman rules in the Lagrangian that involve this ms bar mass, right? Besides other couplings in the theory, right? That will quickly become a differential equation, right? For this guy. And if I find the right boundary conditions for differential equation, I can obtain this guy directly from this demand. And this kind of logic is true even if I don't know this number, right? Which is known for particles that are free and go on shell, but not all fermions are like that, right? Quarks, for instance, are confined. So even this mass is not very well defined, right? And I might be able to get this one, not through this equation, but through the solution of a differential equation like that, right? Also, in one of these equations, these will get connected to other running constants in my theory, right? Which will end up in this scheme to also depend on this parameter, this subtraction point, right? So you see that we'll be able to actually interpret this point as a scale in which I'm measuring all these couplings, right? That's important to remember. This running mass is way more similar to a coupling. Of course, it's a coupling for a two-point interaction, but a coupling nonetheless, right? That depends on this scale that for now has no, it won't have any physical interpretation, but it is a scale where I'm calculating everything, right? And it could be way easier to understand your theory by doing that than trying to write things in terms of a pole mass that might not even exist for some particles, right? And so that's why we'll be very interested in actually doing things this way, right? We'll see that this leads to the equations of the renormalization group, right? But that's a theme for the next videos. I think I said everything I wanted to say on this one. So see you soon.